Dear participants, dear colleagues, I would like to welcome you to the final dissemination event of the research project Integrity Improvement of the Rotorcraft Main Gearbox. My name is Willi Siegel and I act as moderator for today's webinar. I'm an employee of the European Union Aviation Safety Agency and I'm very delighted to be here with you all. This research project has been funded by the European Union's Horizon 2020 Research and Innovation Program, and it was planned in the work program 2020. There in this work program, it was mentioned that the EASA should actually manage this project in the form as an indirect managed project. And to this effect, the European Commission has formally delegated the contractual and technical management of this project to EASA. Now, after a public tender procedure, which we had in 2020, we then finally selected the former ZF Luftfahrttechnik as the best suitable company. This company now has been taken over and is currently firmed as Airbus Helicopters Technik GmbH. And let me also say this research project is part of a broader research and innovation portfolio at the EASA. And we address with such research projects authority needs, aviation authority needs, and these research projects are very important for us in order to do our tasks. So let me now please introduce my colleagues. Next to me, to the left, is my colleague Rodrigo Martin Gomez. He is a senior certification expert at the EASA in the field of rotorcraft transmission. And Rodrigo acted in this project as the technical lead from EASA. Then here is Jörg Litzper. Jörg actually acted as the technical lead from Airbus Helicopters Technik. And Jörg is the head of the Drivetrain Components Directorate at Airbus Helicopters Technik GmbH. And to my right is my colleague Louis Mignot, who acted as transmission expert for this project and was also very closely involved in all the technical discussions. Now, before we start, let me please give you an overview about the agenda. So we will start first with Rodrigo, who will give a short overview about the research scope and the objectives, also some background actually why EASA has selected this project in the first place. And then we will hand over to Jörg. Jörg will give an overview of how the project was implemented and will also inform us about the main results of this research project. Then we hand back to Rodrigo, who will say then what are the main takeaways for EASA and how we will further follow up these research results. And then, colleagues, it's up to you, because we will then move to the questions and answers part of this webinar. And we all are here for you in order to answer your questions. And at the end, we will have our concluding remarks. So before I hand now to Rodrigo, can we please go to the next slide? There is one information to you. We will use Slido. You will have the Slido app actually also in WebEx built in. You see here once more the event code and the bus code. It was also part actually of the it's also mentioned on the events page. It was part of the registration. You can, if you want, already send us the first questions or comments, or you do it then during the questions and answers session. Good. Having said that, I would like to hand over to my colleague Rodrigo for the first part.
So, hello everyone. Good afternoon. So my name is Rodrigo Martin, as Billy said, and I will introduce a little bit where we started from and what questions this research project was aimed to answer. So this is cutting the story short, but just to not keep you losing your time on the background of this project. Basically, the ultimate trigger for launching this research project was the safety recommendations that were received from AIB Norway following the LNOJF accident. This accident was a helicopter accident that happened in Norway in 2016. It involved catastrophic jamming of the main gearbox due to the rupture of the second stage planet gear of that main gearbox, and that was caused by a crack which initiated and propagated in rolling contact fatigue. So following that accident, the Norway issued accident report in which they included a number of safety recommendations for us at the EASA, and this included the need to research into crack development in high-loaded case-hardened bearings in aircraft applications. So you will see this one is directly linked to the activities of this research project. And then another one that is maybe not so clearly linked to the activities of this research project was a safety recommendation referring to the need to develop MGB certification specifications for large rotorcraft to introduce a design requirement so that no failure of internal main gearbox component should lead to a catastrophic failure. So in the case of this particular safety recommendation, we saw some challenges. So you will see that we've tried to do something with this research to identify ways to improve the situation, but let's say addressing directly this safety recommendation was not found that easy. So making the link with these safety recommendations, stream 1 is intended to address resilience of the rotor and rotor drive system to failure of individual components. By this, I'm referring to the tolerance of the rotor and rotor drive system design to continue to rotate, if possible, even to operate in case of failures of individual components. So in order to do this, there were three main activities. The first one was reviewing existing helicopter designs, their configurations and design options when it comes to the rotor and rotor drive system. Then from that review, identify design weaknesses. And in this case, when I'm talking about design weaknesses, I'm referring to those components where a single failure could lead to catastrophic consequences upon the rotorcraft. From these weaknesses being identified, then the following step was to develop alternative configuration and/or component design solutions that could prevent or at least mitigate such failure. So that would mean that, if possible, the failure would be completely eliminated, or if not, that's not possible, at least its severity will be reduced. So that's it for stream 1, which I guess you can more or less trace to this one of the second safety recommendation that I mentioned before. And then stream 2, which is even more clearly related to the first safety recommendation. This stream 2 was intended to deal with the reliability and tolerance to flaws in integrated bearing races subject to rolling contact fatigue. So rolling contact fatigue is a kind of failure mechanism that we had not much experience with. So this was identified in the accident report, and we agreed with that need. So for this activity, we followed the following approach. First, the intention was to gather the state-of-the-art understanding regarding which were the critical design and manufacturing parameters that are involved and contributing to rolling contact fatigue. Within these parameters, just to mention a few, we could imagine operating contact pressure, lubrication field thickness, clearances, surface hardness, case hardening depth, residual stresses, and surface roughness as being considered. When these critical parameters are identified, then the following step would be to also identify which flaws need to be considered. So, of course, when we think about integrated bearing races, they are subject to damages and degradation throughout their lives. So the intention would be to take into consideration potential flaws that could also act as initiating points for rolling contact fatigue crack. So these kind of flaws could include corrosion, scratches, impacts, material inclusions, residual stress variability, grinding burns, micropicking, or spalling. When this step was completed, then the plan was to put together an analysis and testing strategy in which the following need to be included. So inner and outer bearing races needed to be evaluated. Carburized and nitrided low carbon steels were to be evaluated as well, also as inner and outer race samples. Then the impact of parameters that were identified as critical should be evaluated within ranges that were applicable to industry, to the rotorcraft industry. So, for example, if we are talking about contact pressure, testing contact pressures that are representative of rotorcraft main gearbox bearings. And then also ensure that we are having representative loading conditions, considering also other loading aspects such as body stress and residual stress. From that point, then the idea would be to perform any analyses that are needed in support of defining the final test plan to, let's say, fine-tune the geometry, adjust testing conditions, and so on. When everything's ready, conduct the test, collect the data, and analyze the data. Within this analysis of the data, the idea was to include also any additional activities to cover areas where testing was not covering, let's say, all possible parameter values that we wanted to investigate. We would try to use simulation as much as possible to understand better any changes. And then when all the activities were concluded, the idea was to be able to draw the following conclusions. So first would be characterizations of the parameters that prevent the initiation of cracks in rolling contact fatigue. Then the identification of flaws for which crack initiation and subsequent propagation may not be precluded. And last but not least, determine factors that promote crack development back to the surface rather than into the core of the race. So that's it for my brief introduction of why we did what we did. And now I leave you with Jörg Litzba from AH Technique.
Thank you very much, Rodrigo, for the introduction. Now, the following slides, I would like to give the overview of the project implementation and the key results as addressed and commented by Billy in the beginning. I I want to give a short introduction into the agenda of my slides. Of course, I would like to give you first an overview, then go into the details of Stream 1 and Stream 2, and have a summary of the project, and I would like to draw the conclusions at the end of my summary. Now, starting with the overview of this project, I have to say the title was called Integrity Improvement of Rotorcraft Main Gearbox. Since we use some acronyms for the projects, we called it GIFT MGB. As you can see it on the left side, it's taken from the project title. It was already mentioned that the background is the accident of the LNOGF and the related accident investigation findings. And the project was after the public tender run between June 2020 and March 2024. The project team itself was made from Airbus Helicopter Technik as the project leader, with the project partners SKF Aerospace, University of Hannover, Department IMKT, and the University of Paderborn, the Depart WEUZ. There is a project page including the deliverables available, prepared by EASA. You see the title here, so it's difficult to just click on it. But on the next slide, you will see that you have a section for the downloads of the deliverables. Means these are documents showing in detail the results. Now let me start. Now let me continue with an overview. The project itself is split into two nearly independent work streams dealing with separate aspects of the overall project topic. Stream 1 is dedicated to a global review of Rotorcraft architectures with regards to the drive system. And here I think it's the link to the second part of Rodrigo's introduction, the review of the state-of-the-art Rotorcraft gearbox configurations and the component design general, a description and a supporting evaluation of these architectures and individual components, and working out based on these design proposals. And this is then leading to recommendations to future MGB designs where the aim is to prevent or at least to mitigate catastrophic failure modes. Stream 2 itself is dedicated to baseline research with regards to rolling contact fatigue, shortened here to RCF on integrated bearing races, where the focus is on the determination of the design parameters for the component reliability and flow tolerance under RCF, to determine factors that are impacting the crack propagation and the possible crack through. And the activities include analytical analysis, simulation of the rolling contact fatigue and crack propagation using finite element, and of course, significant testing using representative specimen. Now going further into the detail of Stream 1. To give an overview first, the analysis was done with a focus on differences of the configurations, mainly epicycle versus collector, using a failure flow diagram approach, which is based on a potential failure modes and consequence analysis, also considering field experience, but not only in aviation, but also automotive and wind energy, since integrated race-based blended bearings are not only used in aviation. The failure flow diagrams that were developed are using a generic methodology. Step 1, generic failure flow diagram, then further broken down to the MGB architecture, and then further on going to the flow diagram for the single component. The analysis include relevant OEM and drivetrain architectures, but using public data. It's important to name this here because the analysis is based on public data, and the nature of the public data means that it cannot be excluded that any OEM internal analysis based on further details may lead to different results, for example, regarding criticality. At the end, a recommendation for future MGB design, as mentioned, to prevent or mitigate catastrophic failure modes, was done by proposing adequate design solutions and, of course, looking again into the failure flow diagram analysis. First of all, we did the failure mode analysis and we reviewed accident analysis on relevant helicopter accidents in view of root causes and conclusions out of them. A failure mode analysis focused on the load path elements, of course, mainly gears and bearings, shafts also, where the integrated races are used. You see it here in the tables on the left side. It's a big chunk of data that was looked through, analyzed, and reviewed. And on the right side, there is an extract on a blended bearing failure mode analysis, where we have, for example, a lubricant having an effect with having not enough lubricant there, leading, for example, in 43% of the observed damages to rolling contact fatigue topics, for example, by worn surfaces, discolorations, and so on. Now, the review and the analysis of this criticality was done in accordance with the AH-TEC or ZF, formerly ZF experience and knowledge, but under consideration of standard aviation procedures. For example, when we did the severity classification, we used the AC29-2C. To give you an overview of the FFDs, we have the generic failure flow diagram, so the FFD, and you see it's a quite big diagram, which is then further used for the MGB architecture FFD, and then transported and transferred to the single component FFD. In the next slide, I would like to dig a little bit deeper into this. I hope you can see the arrow of the presentation. I try to do it slowly. On top of it, we have started by using and considering relevant failure modes. And this could be a lightning strike, manufacturing defect, material defect, assembly failure, loss of oil pressure, and so on. And we looked to the effect of these failure modes to the parts like gears, bearing, shaft, and so on. And we assumed not to have spalling or micro-pitting, but to have cracking. And by working up through the FFD, we looked whether we can detect it, for example, by a chip detection, chip alarm, or if we have a crack and if we have a potential catastrophic failure coming from the failure modes on the single pass. This was then further transformed into the analysis for an MGB architecture. Now this picture is an example for an epicyclical MGB, where first of all, I would say a simplified architecture overview was being prepared. You can see it on the left side. And then on the right side, this has been broken down to the main, I would say, to the main sub-assemblies. These have then been analyzed into the point where do we expect or where do we find a potential catastrophic failure modes. The difference you can see in the color here, I would say orange here, and if I look on the slides here, it's a disconnect in the load path. So it means no torque can be transmitted, but at the end, auto rotation is still possible. So there's no jamming. On the other side, we have the red indication here. We have at the end also a disconnect. We have a failure, but there we have a jamming, which means we will not be able to have an auto rotation function. You see it here in the FFD by the color code, and you see it at the end, auto rotation or potential catastrophic failure mode. These red marked sub-assemblies are then further used in the FFD analysis to go down to component level. You see it here, the second reduction stage, where we start with a planet carrier, for example. And there we assume that there is a crack of the connection and we walk through the potential effects. Now on the left side, we will end up in MGB inspection, we will end up in power transmission is ensured, so no problem. If we continue other potential failures based on this cracking, we could end, in the worst case, in a jamming of the planetary gear stage. A little bit too fast, sorry for that. And by this, we know the exact path and we know the component on which we have to focus next. Now, this was now very, I would say, methodological. This was more academic. Now let's go to the MGB architectures themselves. I do not want to talk about each of this picture. What I want to say is step one was for each architecture to identify the weakness and the failure modes with the focus on SPOCF, means single point of catastrophic failure. You could see it here in a planetary gearbox. You could have this dotted line here. You could have a crack here. There's another potential planetary gearbox architecture where you have also a crack here, where the planet gear is splitting apart. You could also have integrated raceways on shafts, which could lead to a crack, to a rupture indicated by these dotted lines here. But we also have, for example, architectures in the Rotorcraft, where we have, for example, a direct connection from the engine to the MGB, which means we have a direct connection, let's say, which needs to be considered and a failure in this connection from the engine to the MGB. On the next slide then, we have step two. we do the impact analysis according to the presented FFD, and we look, as I mentioned, to the potential catastrophic failures according again AC 29.2c. So you see it here, this FFD would lead to a catastrophic failure. In the step 2b, the development of the safety barriers, we call it safety barriers, was done, and it was checked in an additional FFD analysis if these design changes, these safety barriers would lead to a non-catastrophic failure at the end. If the FFD analysis, the result would change. To make it more, let's say, applicable to a certain application, I have here an example of a planetary system where we would have at the end a jamming of a planetary stage. And we have several possibilities in this architecture to avoid this jamming. For example, introduction of non-integrated bearing as a safety barrier, or the definition of the side parameter to avoid the crack growth into the bearing, or a design implementation to support ejecting of particles from the gear mesh, which means to avoid the jamming. Having done this, the next step was to do step 3, the pre-designing and the detailing of these safety barriers, and to apply it to this existing concept, to this existing architectures. For example, here you see it on the left side. There, number 20, it is the introduction of an inner bearing, so there is no integrated raceway anymore. In the middle, on the top, there is a so-called bordure retaining ring, which means it would hold the planet parts together, and the planet parts could not go into the meshing, it could not jam the planet gear stage, for example. If you go down, for example, for a shaft, so no planetary solution, a collector solution, this is now number 5 here. There's a so-called jamming preventer introduced. It's sort of dedicated shaft which would support the shaft in case of a rupture. This means there's also no jamming of the gearbox. We also looked into generic or Rotorcraft architectures. There are several options. I do not go into the details for now. It can be looked up in detail into the deliverables as mentioned before. After the design has been completed, we needed to evaluate somehow, we need to look somehow how realistic are these concepts. So this is step 4. It's the application and the concept assessment and the prioritization of these several design solutions. Why? Because we needed to check further which impact such a design solution has. For example, is it feasible anyway, or is it just a wild idea? Are there boundary conditions? Are there obstacles that you need to consider if you want to apply it? There's also a question, what is the most promising solution, and are there any economic aspects to be considered? I do not know, 10 parts more to be manufactured or something like this. But there are also disadvantages or advantages. For example, how significant is the influence of level of criticality? And what is the impact on, for example, the weight, the size, or the number of quantity of parts? In detail, the project delivered such a matrix with the solutions, the description, the evaluation, and I would call it a certain ranking of what has the highest potential. Now this ended already stream 1, which was more focused on really the gearbox architecture at the end. I would like to continue now with stream 2, which is focusing on the rolling contact fatigue and the influence on the crack initiation and the crack propagation. Again, I would like to start with an overview to give a rough idea of what I'm going to talk now in the next minutes. The investigation here is focusing on fundamental understanding and let's say the further use of the crack propagation on integrated raceways that are under rolling contact fatigue. Part of the stream was the analysis of available literature and field experience coming from relevant applications, to see which influence parameters are there, to look for state-of-the-art design methodologies, but of course also to have the lessons learned from accidents and from other investigations. A test campaign was performed using representative samples for helicopter MGB design, which means dimensioning, material, manufacturing, loading, and so on was considered, where we had the, let's say, the necessity to specify the test specimen, the test conditions, and the test benches, and then manufacture the specimen, test accordingly to the test plan, and do a very deep analysis of the test results. In parallel, and also for validation, for verification of the testing, of course, and vice versa. We prepared an FE model definition and validation where we implemented the relevant parameters, for example, residual stress condition, loading due to rolling contact, and no body stress, and we performed simulation of the crack propagation also for various parameter settings. The FE model validation was partly based on literature because observed cracks were checked if the prediction is correct and so on. And we also looked if the FE model is predicting correctly the results of the test campaign. Finally, there was a definition of recommendations done with regards to future design of MGB. Was already mentioned influencing parameters or a general method how to deal with this topic rolling contact fatigue and crack initiation and crack propagation. Now, first of all, we needed to look into the design criteria and the related parameters. We did select here, let's say, the starting point as a review of the experience on design parameters for typical aviation application with the focus on relevant type of bearings. Mainly here, SRBs, CRBs means spherical roller bearings and cylindrical roller bearings. The project team discussed known field failures and observed failure modes, also including a cross-effect analysis of these design parameters, which then led to a fishbone analysis on crack initiation and subsequent crack propagation, including and of course the damage, where relevant aspects from the previous analysis was taken into consideration. And finally, each parameter was evaluated concerning the criticality with regards to the crack propagation, crack initiating, crack propagation. We selected low, medium, high to have not 1 to 10 or 1 to 50 grading, but we prepared a matrix where we said, for example, we have a parameter. Let's take one of the prominent examples, residual stress, for example, which has clearly a high criticality with regards to the open technical question. And then we have a rationale here why we rate this as high. Now, for example, here, if you look to the residual stress, change in stress level would lead to decreased flaw tolerance. Each of the parameters analyzed are in this matrix. You will find the rationale here in the documentation, and this was the baseline for the next steps. The next steps was then how to, I would say, how to deal with the various aspects and how to look into the rolling contact fatigue that is known from the past, the crack initiation, potential crack propagation, and potential crack through. The project decided to develop 3 main hypotheses based on the mentioned analysis and detailed literature research. First of all, first hypothesis, in case of a pure rolling contact load, an ignition of a crack with a finite depth may occur. But this means the crack growth ends at a finite depth. A crack typically leads to spalling damage, and this crack growth towards the surface is known for pure RCF. But of course, crack growth into the material is known in combination with a second driver. This is then leading to second hypothesis. Without a complex load situation that is present for example, in the planetary gear, there will be no further crack growth into depth under a single load of the rolling contact. And finally, of course, under the complex load situation, if we have body stress, a crack propagation into the material is possible and has to be considered. These 3 main hypotheses were then further used in the specification of the test specimen, and the test specimen are required in accordance with the 3 main hypotheses. In the project, we needed a clear separation for the test campaign. This means the test phases are named accordingly. Phase 1.1, pure rolling contact fatigue for different contact pressures. Phase 1.2, rolling contact fatigue plus maximum contact pressure, including a variation of relevant parameters. And phase 2 is the complex loading. A parameter analysis was further done as a baseline for the test specimen, having the following targets. We need to ensure that the samples are representative. It should cover the widest possible range of parameters that are still acceptable, no? Because we need to look also to the statistical analysis of this testing. It should consider, of course, aviation typical application, for example, material loading, and we need to give prioritization to design parameters in view of a project target and expected impact. Why is this important? If you look to the right side, there is an overview of a parameter analysis for SRBs and CRBs. And we see that we have already here a number of parameters that are typically used for the design of such bearings in an aviation environment. And we needed to look which one are the most prominent, the most important factors for the next steps for the testing. For example, we have the contact stress where a certain range is, I would say, best known in the industry, for example. Or we have residual stresses that are also typically applied. So this was the baseline. This was the baseline, of course, only on the micro level. We talk about contact stresses, about micromillimeters, we talk about stresses in the part, but we need, of course, also to look to the macro level to have a representative sample. And therefore, we made it quite easy. We looked to the MGB analyzers, of course, done in Stream 1, for example, and we looked where do we have the integrated raceways typically. For an epicyclic design of an MGB, I think it's obvious we have the planet here. On the planet here, you see it here, it's a CID modeling just for representative reasons. We have the test specimen called ring in a version, standard ring and ring with a notch. For the complex load situation, I will come to this later. And if you look at the collector design, for example, we take a shaft, and on this shaft we could have integrated raceways. And since it is a shaft, the test specimen is called shaft in the version non-hollow, and hollow, of course, here too for the complex loading, introduction of body stress, and so on. A transformation of all of these aspects was necessary with regards to the number of specimens that we needed. So you have seen that we have heat treatment, design parameters, and so on. But of course, we need to select the number of test specimens in a way that we can handle it in the project time and in the project scope. Yeah. Based on this samples, this number of samples, we said that we will spare 3 additional specimens for phase 2 for the complex load, but selected based on the results of phase 1. Manufacturing parameters mentioned before already, selected in view of processes for comparable parts, means standard aviation. But we needed an additional process step for the notch that was mentioned to ensure that we have the good, let's say, ovalization, the body stress, and so on. And therefore, we selected EDM, electric discharge machining. One remark here, the white layer of the 32 CDV13 inner ring specimen has not been removed. Yes, but this was a project decision based on some aspects that were discussed in the project team. And of course, as all of us, I think, know, if we have a manufacturing, sometimes we have a slight deviation, a little bit outside on this side or a little bit too low, but all of these deviations were acceptable and was checked and had no impact on the test results. The table on the right side, they give you a rough overview of the specimen called inner ring and outer ring. The inner ring is actually the shaft specimen with the several variants that you see here that were tested. The materials reaching from 16 NCD13, 32 CDV, but also M50 And you see here the manufacturing approach from a basic variant to adjusted heat treatment and so on. And you also see here which specimen in which condition was used for which test phase. Now we have just a short words about the test specimen. This test specimen ring, you see here a bearing, yeah, but the ring specimen is at the end the outer ring. Yeah. This is the ring which is the standard ring for phase 1, and for phase 2 in the complex load there is a CAD picture for illustration here. You see here on the outer ring the notch. So this is the notch here which I mentioned, and this outer ring of the bearing is basically replaced by this modified outer ring. On the shaft, I think it's obvious here that we have a non-hollow shaft, a solid shaft, and a hollow shaft. Before we did the testing, let's say the live testing, we had some test specimen and we used some standard indents which are comparable to some overrolling, some indents which you could expect. But we saw that the initial damage, the spalling that we need, took so long that it would not be feasible in the time frame of this project to wait for this spalling, which is also a little bit not predictable. Therefore, it was selected to have a pre-damage modification to to ensure a plannable and reproducible spalling damage. And this was done by an indenter with a diameter tip and a force of 100 Newton. So we can, in each test, ensure a classical spalling damage in a, I call it short time, but it's an overall testing time that we needed to do all the tests in this project. And this was then the leading, this was leading to the starting point for the potential cracks, crack growth, through cracking, and so on. So you see here on the left side, you see the scratch. On the right side, on the first picture, you see the indenter. And as you look on the example of the raceway here, you would see it like this. It could be even a real part. If you just have a screwdriver and somebody is going over it, you would have a certain scratch. Just 2 words on the test benches. We have a test bench called outer raceway and inner raceway. The outer raceway, it's belt driven, you see it here. They are comparable small test benches. Now, as you can imagine, we have a shaft supported by 2 support bearings. In the middle, we have the mentioned test bearing with the test specimen, the outer ring at the end. The other test bench on the right side, it's also comparable small. It's the inner raceway. The inner raceway is here. It's the shaft specimen where we have the test bearing here, the integrated raceways on the shaft, and we have the support bearings here. And just to give you an idea about the sizes, the bearings are type 206 bearings, which are also typical bearings used for any other bearing test, bearing research project, and so on. So comparable small. Now coming to the test campaign for the results for phase 1.1. You see here the pictures that we observed. Typical spalling damage was observed for all specimens at 2.4 gigapascal. For the 32 CDB13 shaft specimen, we had a peeling of the white layer, so not a typical spalling, but a peeling. And you see it also here in the picture on the right side. There was no spalling at 1.8 gigapascal or 1.5 gigapascal, and there was no crack propagation into the depth. You see it here, we made pictures from the spalling damage. You see also the scratch here. The mouse is a little bit slow, so I try to go over it. And then we always evaluated these damages by metallographic cuttings, also to look in a way, do we see some subsurface or some cracking, and you see it here. The cracks, they are resting always at the same final depth here at the end. Yeah? But at the end, it was always spalling. Phase 1-2, we had a variation of hardness, the hardness depth, residual stress, and so on. And we saw a variation in spalling depth. We also did not notice a crack propagation into the material here. And the results are generally comparable to the phase 1-1 results, which means a crack growth ends at the final depth, mainly in line with the spalling depth. Just an example here on the left side of the residual stress and the hardness measurement results that was done, also to verify that the manufacturing settings, the desired targets that we want to have, are met. On the right side, you see the evaluation of the maximum detected spalling depth for 16 and CD13 and the peeling, as I mentioned, of the white layer for the 32 CDB. This is the shaft application. And we see some influence. You see it here for version 1, it's a depth of 0.3, whereas it's 0.1 to 0.15. You see also on the peeling of the white layer a difference. Now the question is, based on the statistics, if this will remain if we test 10, 15 or 20. There is a small result noticed, but I have to say it could also be that is for the 3 tests, maybe only 1 result. But there is a difference to the outer ring application. The observed influence is not that drastic as for the shaft, for example. And you see on the right side bottom, you see it for the outer ring application. It's always plus minus 0.4, for example, here. No? So the spalling depth on this is more or less comparable and the same. And then we went on to the phase 2. And for the phase 2, the complex loading, we started with the shaft testing. And for the shaft, first of all, we didn't find crack propagation into the depth, so and for sure not through. Yeah, so in depth, yes, but not through the part. And we first started with the standard indenter scratch, as mentioned before. but this just led to the same damages as before spalling, so nothing else. To provoke crack through in the part and to, let's say, help the part to be more critical, we decided to modify the scratch and to add a deeper damage by laser to initiate a more severe crack initiation, to have the crack through propagation promotion as a pre-damage. You see it here on the right side on the upper picture, the shaft with the laser introduced damage, and this is after the test with 2.9 gigapascal. Below you see it here with the 32 CDV. You see the same, you see the pre-damage and you see the crack growth, but whatever we did, we didn't achieve a crack through of the part. So for the shaft application, we saw spalling damage. As you see it here, the surface is spalling, peeling, but even with this large crack initiation, it does not lead to a crack through of this component. If we then go further to the outer ring, we had a crack through detected for M50 nil at 2.4 gigapascal, and the 32 CDV 13 crack at 2.9 gigapascal. In general, we noticed a difference in spalling behavior, and you can see it here if you compare the complex and the non-complex load situation. The green one is the non-complex, phase 1, and the gray one is the phase 2, the complex loading. You see the significant change in spalling depth. And for the M50 here, for example, it's quite clear that you see a complete breakthrough. So at the end, finally, we had a result which showed us that the test setup is leading to a crack through, but it was, I think, overall harder than expected to get this cracking damage. In this overview here, you see the tests being performed with M50 nil with 32 CDV13, and you see a slight variation on the notch here. You see also that we had several quantities and we had a pre-test done. You see it here, the pre-test. Oh, sorry for that. Go back. For the pre-test, for example, we had a spalling with a through crack. And if we then, for example, look to the same test here, we had the spalling, but no cracking through. So we had some problems here to get this cracking, which was further analyzed. But at the end, you see that you can initiate the cracking. Now this is the test side, and I mentioned before that in parallel we also look to the simulation side. And the simulation side, I would say, of course, to handle each effect, we have the helicopter, we put the full MGB in, a full 3D FE model with a lot of nodes, with a lot of details in the mesh, but this is quite huge. You could use a sub-FE model of a rolling contact area, here focused of course on the buoyancy, but even this would lead to significant long calculation times. We checked it in the project, and due to the needs of the project and due to the desired simulation content, we did a model reduction. We transformed it into a representative 2D model, which was used for the RCF and crack propagation analysis. Nevertheless, of course, further on for generic design, for analysis, it's always possible to go back from the 2D to the 3D. But for this project here, the 2D approach was the good approach, and I would like to show this on the slide here, because in the next slide you will see the general approach for the crack propagation analysis on an example for the FE model for the complex load situation of an inner ring, the hollow shaft, and of course the ring. Now, if we look to the left side, I hope you see the mouse, the arrow here. If I make a line here, this is applicable for phase 1 and for phase 2, which means we have the setup here, we have the rolling element, we have the mesh defined to analyze this area. You see the rolling contact zone, we see the edge crack, we see the crack initiation, and this is used as an input for hollow shaft for the hollow shaft, but also for the ring, for the ring with notch and so on. And the second part, the right side at the end, is of course due to the mentioned phase 2 for the complex load is more applicable for this. And you can see it here at the end, the boundary conditions, the contact zone, and the model used for the analysis. You see it also here, the ring with the notch transformed into the CAD and the FE model, where in this very, very small area here, which is indicated by the red arrow, the crack initiation would start. We have mentioned already the importance of residual stress. So we implemented the residual stress into the FE model by using a thermal stress approach. And we did measurements for this. And yeah, to show you one example, we selected the hollow shaft, but it's also valid for an outer ring. Yeah. On the left side, you see the cutted parts, and you see the measured values for the residual stress. And it was measured from both sides, from the inner and the outer diameters of the raceway. This is then taken over this data into the model by thermal stresses, and ending up then at the end in the full model means we have the ring, we have at the end also then the loading by the RCF, but also including the residual stress. Based on the pre-work of the FE model, and of course then let's say the setup of the calculation, the crack propagation simulation analysis has been done. I would like to start with the analytical description on the left side. The calculation of the stress intensity factors K1 and K2 and the equivalent stress intensity factor KV was done on the crack front for each simulation. Now let's look to the picture here. We have the rolling element and the outer ring. We have the initial crack length, and then you will see here different colors. Yes, and each color is representing one simulation step, one increment. So this means it's one calculation, then the next calculation, the next calculation, next calculation. This means for each of these crack fronts, yeah, this has been done. The crack propagation threshold that is used here, which is given in the diagram here as the red line, is selected for the purpose of this project according to literature, data sheets, and so on. It was not a desire, it was not a target to define it or to challenge it and so on. The crack growth condition is delta KV larger delta KT. If it is growing, then this must be fulfilled. The calculation of the crack path for the crack stop is at the end, you see it here, it's the opposite. Yes. And if we see a decrease in the delta KV with the crack growth, the crack stop is expected. Now let's go back to an example here. This example shows the crack growth simulation of the outer ring. It shows crack branching and crack growth parallel to the surface in both right and left directions. So I go back here, I just mentioned it. So this is the left side here, the decrease in crack loading on the left track. So close to the value of delta KT, so the crack growth should go to a standstill. On the other side, the crack loading on the right is smaller than delta KT, so the crack is a standstill. And these two sides are further shown here in these diagrams. So you see the max delta KV over the delta KT. Then you will notice that the one is above the red line and the other one is below the red line. Coming to the comparison between the results and the simulation. I start with phase 1. We have the rolling element, we have an initial crack of 0.5 millimeter, and you see the just mentioned increments, the calculation of the crack steps. And what we see is, or what we saw in the simulation is, after the crack branches, the crack stops. No crack through, the crack propagation in the depth of the material is limited, so it's a finite depth. And we would expect spalling, and at the end in the testing we observed spalling. No crack growth into the depth of the material, only, as I mentioned, if we cut it through, we have these finite depth crack, small cracks, but it's in general a good correlation to the simulation. For the phase 1-2, we have the same initial crack of 0.5 millimeter. Again, the crack path was simulated. You see it here, we would expect again spalling from the simulation. and you see it here where the arrow is the metallographic cutting of the sample. We see a spalling. The crack propagates only up to this final depth here. I mean, if you cut, you see here these small cracks, and it is only limited, but there's no crack through. So the simulation and the testing also correlated quite well. Coming then to the phase 2. Phase 2, at the end, the results of the FE simulation have been compared to the test results, both for the inner and outer ring samples at the end. The results for comparison to the test results for the hollow shaft with the latent scratch, I would like to start first with. Each analysis is again based on metallographic analysis of the test specimen to check for the crack propagation in the depth. It's the 2D crack growth simulation, as I mentioned before, in the ring with the notch, also to see what is happening in the depth. And we compared qualitatively both simulation and the testing, and as you can see it here on the pictures, it's also correlating quite well. We have the predicted or the pre-damage, we have the predicted direction of the growth. And if we look to the testing, we also have the scratch. Of course, we have some surface damage here, but the crack propagation in the cross-section of the metallographic cut is showing it's correlating quite well to the expected direction. Coming to the ring, to the sample here with the notch. Again, here the analysis is also based on metallographic analysis of the test specimen. The crack growth simulation has seen, of course, the same loads as in the test, as it is done also for the other comparisons. The comparison of the predicted crack path using the FE simulation was done, and we expected at the end a certain crack growth. So this was expected. Now you see the crack propagation phase 1. This is meant with 1 and 2 in the wording here, and we have a direction change here at the end, which is the part 2. Yeah. If you would put this on top of each other, you could say again, it's a qualitative good correlation between the simulation and the testing. But of course, it's cutted, it's arranged, but qualitatively, I think the depth and also the direction fits quite well. After doing all of these analyses and studies and a lot of internal project discussions and also discussions, of course, with the specialists here from IASA, we developed a methodology for the rolling contact fatigue assessment with regards, of course, to the project goal concerning crack propagation, crack initiation, of course. Based on the content of this research of the GIFT project, we established a methodology that is shown here. This methodology aims to provide support for compliance demonstration to CS27, CS29, 571 paragraph for certification of integrated bearing races with catastrophic failure modes. Now, the approach itself is based on 4 main steps. I want to excuse because it's difficult to read, but it was the only possibility to get it on this slide here. I will try to explain it. Step 1 at the end is the evaluation of component design values. It's the geometry, function principles, known failure modes, geometric data. Evaluation of external loads, for example, contact pressure, bearing loads, temperatures. Material properties, also of course related to the crack propagation, crack initiation next to the standard material values. And of course, measurement of and evaluation of residual stress profile, since this is the baseline data of a component that you want to use, that you want to design, that you want to reuse, whatever. Point 2, or step 2, is the collection of additional MRO data and use of the experience from the GIFT project. Now, what do we mean with this? Each of us has MRO data. For example, do we see maximum spalling depths on components? Do we see damages? Do we see something which can be linked to, for example, maximum contact pressures and so on? From the GIFT project here, we could take over the initial crack size and depths or the initial crack angles, for example. Step 3, which is probably the main design step here, is the setup of the FE simulation and a potential recommendation for a redesign. We set up the FE simulation we evaluate, we check if track growth is possible, yes or no. And based on this, we have to decide whether to go to a redesign. No? Then we would start up again. And if we do not see it, of course, it could be a support for the certification, for the qualification. But validation, I think, is needed by testing, or at least will be supported because of the nature of this failure mode and the knowledge up to date. So I would expect that this testing plays a big role into certification. Now, having talked about the Rotorcraft architectures and the rolling contact fatigue and the testing, I would like to summarize the project. First of all, in-depth analysis of the current state of the art helicopter MGB architecture was performed based on a failure flow diagram approach, and design modifications to prevent a single point of catastrophic failures were proposed. The damage mechanism and failure modes of bearings used using integrated raceways were analyzed, and these results were used for the definition of representative test specimen, condition test benches, and followed this, as I explained, the test campaign was performed. Afterwards, the impact for the design and manufacturer was analyzed, and it was checked how the RCF and the crack initiation is progressing, and if we have a crack propagation or not. The mentioned main hypotheses concerning RCF and the development of the crack propagation were at the end confirmed. Based on in-depth analysis, an FE model for crack propagation was developed, and in the scope of the project, it's validated. Now, validation is a big name, but in the scope of the project, we consider it validated. And the validation is performed using data from literature, but also by comparing with the test results within the project. Final achievement of this project is the methodology, which is supporting or can support CS27, CS29, paragraph 571. That was developed, and it should allow the designer in an early stage a check if there is a risk for crack growth on indicated raceways under rolling contact fatigue, yes or no. Now, Rodrigo said in the beginning that we have to draw conclusions out of this project. So I would like to have some conclusions from our side here. With stream 1 of this project, a representative analysis of current helicopters MGB was performed, indicating, based on the public available data, that a single point of catastrophic failure is possible in each architecture. But it can also be said that design solutions are available to mitigate, yes, and by analyzing of these opportunities, we have the means to avoid such single points of catastrophic failures. However, as each design change or modification may have a negative or a second point, it needs to be analyzed in detail if there is an effect on weight, on size, on reliability, and even not being part of the project, what about a cost at the end? Within stream 2 of the project, a methodology was developed that allows the designer in an early stage to evaluate the potential risks for crack growth on integrated raceways. And due to the nature of the discussed failure mode, each single design has to be analyzed separately. The methodology is contributing to the CS27, CS29, paragraph 571, and may or probably include test procedures that have been developed during this project. Test results have shown that crack propagation through the material, for example, resulting in a split planetary gear, is only possible under a complex load separation. After evaluation of the results and also discussing, let's say, the number of testing and all the aspects we learned through this time in the project, we recommend follow-on research to extend the knowledge gained during this project, since some technical aspects could not be discussed and analyzed in the recommended depth within the defined project scope. And additional work should also include further testing for statistical reasons. We would like to test further, but the tests were quite time-consuming, and due to this, of course, it was a limit with all the variations to test maybe 10, 15, or even more samples. Having said this, I would like to say thanks. I would like to say thanks for the support during the project time for the team involved at EASA, the project partners at SKF Aerospace, the IMKT from University of Hannover, University of Paderborn, central R&D of our former colleagues on the ZF Friedrichshafen AG, of course all the colleagues at Airbus Helicopters Technik that helped us, and everybody I have forgotten, maybe even delivering the packages to us where we urgently needed the test samples to support it and to help us to finish the project basically today. If there are any questions, please write them down into the Slido, and I'm happy to answer them if it's linked to the part here. Thank you very much.
Thank you very much, Jörg. That was an impressive presentation of the research carried out in the last 3.5 years. We have, for the time being, 3 questions already received. I'm sure there will be much more. Before we come to the question and answer sessions, I would like to hand over to my colleague Rodrigo, who will say some words how EASA will now treat these research results and what kind of benefits we take out of it. Please, Rodrigo.
Yep. Thank you, Willy. Thank you, Jörg. So, yeah, what do we take from this research project? So, from stream 1, I would say the main conclusion for us is that for most of the single points of catastrophic failure that were identified in the review of existing designs, it is possible to introduce mitigating solutions, so designs that will mitigate or remove catastrophic failures from main gearbox designs. So that's clearly possible. Some of the let's say tools or approaches to do that would be providing additional support to prevent jamming in the event of rupture of gear or shafts, so that to prevent that either the parts will distort or release large fragments that could lead to jamming. Other options would be to implement shear sections that would allow the free rotor rotation in case of jamming of some sections of the gearbox, as well as emergency drives that will take over when there is a disconnection from the main power source. So these are some examples of general design ideas that could be introduced for preventing or mitigating currently existing catastrophic failures in helicopter main gearboxes today. However, it's clear that preventing or mitigating all possible catastrophic failure modes within existing design should not be considered as feasible or practicable as of today. The main reason for that, in our view, is that mainly, I mean, this has been a pure design study, so that there has been no testing to validate the capability of these design solutions to actually provide the capabilities or the improvements that were assessed just by looking at the design and trying to propose alternative solutions. It has to be said that those capabilities are not clearly a given. They are associated to a specific design structural and functional capabilities, which need to be demonstrated at this stage to our eyes by test. So obviously that would be significant impact if you have to do that for every single alternative design solution that you introduce on your gearbox. Also, there will be a huge impact on weight if you were to remove or mitigate or possible catastrophic failure modes. And in addition, and to my eyes not less important, there will be added complexity. You will have more parts, more interfaces, and that could have an impact on reliability, which is also part of safety. So this is, to our eyes, how we see the end of stream 1. So it's clearly indicating there is room to do things, however, making sure that there's no catastrophic failure possible from failure of individual components within main gearboxes. That does not seem feasible to our eyes. Just a note, the designs that Jörg briefly touched on and that are available in more detail in the deliverables on our webpage are EASA's intellectual property, and they are now public domain, so they are free to be used by anyone, in case you are wondering. And moving on into stream 2, I would like to start with some high-level conclusions. So first, I think it's reasonable to conclude that in the absence of significant body stresses, so stresses within the whole section of the integrated bearing race, it seems that that's enough, or should be enough, to preclude deep crack propagation in rolling contact fatigue, and as such prevent through cracking and rupture of the part, at least when due to this failure mechanism. It also seems possible, even though we realized we did not really have the time and capabilities to develop them. It seems it's possible to develop a threshold for spalling initiation and propagation in the presence of flaws. However, it seems that this is very much application specific. So depending on many variables, one of them being the specific flow for which you are trying to identify the threshold against. But it's clearly possible that when you appropriately replicate your design in a test specimen, you could ensure that you demonstrate that you are tolerant to certain kind of flaws developing into spalling. Going back to the flaws, it was part of the tender specification to assess greater range of flaws. However, this was also some of the limitations we faced. At the end, we had to cut down on the number of flaws that we could assess because of limitations of number of samples, test running time, and so on. So in the end, one of the, let's say, open points would be that a greater range of flaws and any difference in how they impact crack propagation and initiation is needed. And then the last high-level conclusion for us is the key role that residual stresses play. So an accurate quantification of those residual stresses, which would typically require measurement, is very important when doing this type of assessment, to make sure that you understand where you sit and which are the conditions that your design is having to sustain. Talking a bit more specifically about testing, it's clear for us that testing is an effective way of assessing the impact of rolling contact fatigue on any given design. However, a very important aspect of this testing is ensuring representativeness. Jörg only touched briefly on this, but when we were doing some tests with the shafts and with the outer rings, there was some results that really we could not explain There were some samples that sometimes will crack through rather quickly. Sometimes they will only spoil, and this is something that it's difficult to explain. But at the same time, we found some samples that seem to behave a lot better and to provide repetitive results. So yeah, and also more importantly to, let's say, behave more in line to what the simulations were predicting. So that is just to say that, okay, it's possible to test, but it makes no sense to just prepare a specimen and put it into a bench with some kind of damage and just run it to see what happens. You really need to make sure that what you're doing is actually going to represent your design properly. Then we could not find any explanation, and we don't have for sure enough evidence to confirm this, but it seems that through cracking of shafts, or so let's say inner bearing races, is less likely. This is not, of course, any confirmed conclusion. Is just more an impression and would require further testing for validation. It's what our testing suggested, but it's also true that the loading conditions of both the outer ring and shaft samples were not equivalent, so it's difficult to validate this conclusion, but nevertheless, it's something that we take on from this project, and we will see in the future how we can validate it. Regarding simulations, it's clear for us that simulations are a powerful tool. However, there are further developments needed in order to be able to fully rely on them. At this stage, from our perspective, they have to be heavily supported by testing, in which you basically use the simulations to move slightly away from what you are testing, but never to replace testing. Also, we found that really with the tools we could identify, crack initiation could not be simulated. Also, we found it was very challenging to detect it during testing, so that we could stop the test when the crack had just started, and we could investigate that stage of the failure progression. So yeah, crack initiation has been a bit difficult to tackle. Then, of course, maybe this is not a big discovery, but the behavior of the cracks in the simulation seem to become a lot more similar to those in the test, when the cracks were more dominated by mode 1 crack propagation. So the cracks were deeper and less subject to shear stresses, and more subject to, let's say, opening of the crack. And for us, this is what maybe is more relevant when the simulations were simulating cracks which were dominated by shear, so close to the rolling surface. The simulations seem to work quite well to predict what could happen, so predict that the crack could kink or that it could branch into several cracks, but at the moment the tools that were used for this research project, at least, were not capable of making that differentiation of when would it happen, when would it not, and how to determine how the crack will actually behave in detail in these conditions. However, for detecting that when this was possible, it worked quite well. And then, let's say, for what concerns us as a certification authority, we also take some considerations for our future work. So for us, the outcome of this research project shows that it's possible to develop a valid approach to evaluate the risk of cracking due to rolling contact fatigue, and that this would typically require testing and simulation. However, it's true that, as I emphasized before, it's quite important that when you address your specific design, you ensure the applicability and representativeness of the testing and simulations you are doing. So this was a general note that the approach and methodology that has been followed for Stream 2 for this project seems to be generally applicable. However, it would make sense to discuss it on a case-by-case basis to make sure there are no other considerations to be that apply. And then our last consideration regarding certification would be again what I just mentioned, that at this stage we believe that testing and analysis are needed, and that any analyses are sufficiently correlated, because at the moment, as I said, we cannot fully rely on simulations for rolling contact fatigue. So this is it from my side. Thank you very much. And now we are open to questions.
Good. So thank you very much, Rodrigo, as well. Colleagues, if perhaps we can take the next slide, please.
Oh, yes, sorry.
Colleagues, here once more, for those who came in a bit later, this would be the QR code, the event code, the bus code, in order to raise your questions. We have, for the time being, 5 comments. The thing is that the first comment actually is the one which has received the highest number of thumbs up. And if there are an equal number of thumbs up, it is always the first question in the sequence. Then let's start with the first question, and I will highlight this one. It's from Dario, and if I'm not mistaken, this question was linked to the slide, page number 35. Yeah. I think
I know.
You know which one this is. So why was the white layer not removed after the 3D decade?
Yeah, the white layer was not removed for the shaft specimen. For the ring specimen, we removed it. In the shaft specimen, we had several discussions, since we know from other applications that white layer could have a positive impact on the strength. And in the project, when we discussed it, finally we made a decision and we let it on. So it was a project decision based on several discussions, but it's a valid question, and thanks for asking them.
Thank you very much, Jörg. Let's move on to the next question, which is from Scott. When discussing the design of the planetary, adding a jamming preventer was mentioned, but no mention to avoid using high contact ratio geometry on the planets and ring due to the probability of jamming due to geometry interference if a split ring occurs. Jörg, I think this is also up to you.
Yes, this is up to me. First of all, I think there is a mixing of two things. The jamming preventer is not something for the planetary. It is mentioned for a shaft, typically on a collector design. Maybe this was not clear on the picture. So if this was the case, sorry for that. The high contact ratio gear geometry, I think it is mentioned the gears itself, with the high ratio. Actually, we do not found something which is negative to this. on the gear geometry, you can design the gears in a way that the backlashes, that the tolerances are given in a way that they behave like any other gears. But of course, you need to take care of this. But this was not part of any recommendation.
Thank you, Jörg.
Yeah, I think maybe to expand on I know why Scott is asking what he's asking, so I wanted to expand on that. Maybe to say that in that case it will let's say it could solve some particular failure modes. In this case, we did not go into the details of do we consider that the crack is only here and therefore the part will behave in that way. Let's say the considerations we did when analyzing the failures were more at a high level, so we were trying to remove the failure completely. So in case of opening of the planet gear, it's not only that you have a crack and the planet gear opens and is no longer capable of transferring load, it's also whether that could lead to any other cracks and release of large fragments and these sort of things. So it's not limited to specific and detailed failure modes, but more, let's say, trying to remove completely the possibility that something would happen, regardless of the details of that failure scenario. I don't know if that was clear, but I hope it is. But for sure, it doesn't mean that other design solutions would not be applicable. This was just an exercise, let's say, at a more high level.
Thank you, Rodrigo.
Yeah, no problem.
Before I move on, anything to add?
It's okay. I hope it has answered the question from Scott Poster, I think.
Good. Yeah, it was from Scott, exactly. Good. Then let's move on to the next question, which is from Sasha. Why use a delta KTH of 150, where only macroscopic cracks investigated short crack growth usually starts with a delta KTH of 427?
Yeah, I think it's because we investigated these cracks at the end. So as I mentioned, the value can be selected in a way what you would like to investigate for this application. It was decided to go through this value, and the focus was on this type of cracking. It was, as I said, it was not an investigation what is the best version, this or the other one in this phase.
Good, thank you. Anything to
No,
add to that?
there's nothing I can add.
Then we have, I take another one from Nicholas. A question probably to you.
Yeah, this is for me, Rodrigo.
Following this research, will EASA tend to update the expected failure modes of bearings and raceway and propose an update of the associated norm and regulation? Or the results are deemed consistent with current practice?
I would say that at the moment we don't have enough material that is pointing us in a clear direction on how to provide more specific acceptable means of compliance relative to what we have and recently published on rolling contact fatigue. For me, it's clear that probably there is room to a more focused approach. However, at this stage, I don't think we have all the information to say, okay, these are the characteristics and type of designs that we would focus on for addressing rolling contact fatigue, and these ones we can exclude. I don't think we are quite there yet, but of course it would be a direction in which we would like to go, yes, but not possible just with the information from this research project, of course, although it's clearly suggesting certain directions, as I previously said.
Thank you, Rodrigo. Anything to add?
Maybe just regarding the points on the expected failure modes of bearings and raceways. I mean, we already mentioned in the AMC to CS27 and 29, so AMC 1 for 27, 29, paragraph 571, that we may expect somehow crack through in some cases, especially for integrated raceways, and these have to be somehow evaluated. So maybe there is no international standard or something like this, but somehow it's something that needs to be anyway considered for compliance demonstration to paragraph 571.
Thank you, Will. Then, colleagues, let's move on to the next question, which is from Agrigello. Did you notice any correlation between effective case death on spherical race and crack mode propagation?
No, I think we did not have a correlation to this because we looked to the spherical bearings and to the cylindrical hollow bearings, but we did not look to a specific, let's say, case that links to the crack mode propagation. This was not done, not in this detail for the bearings. And for the testing, of course, we didn't have spherical, so it was only coming from literature study what we did for the failure mode analysis in the beginning. But on the test bench itself, we had only cylindrical roller bearings, not the typical small 206 type bearings. So unfortunately, no input for Mr. Barletta on this side.
Good, thank you. And Agrigello, I think I saw also you had this question on the chat, so this is answered, yeah? Then let's come to the next question, which is from Will. Thank you for the presentation. Can you confirm that you did not observe deep cracks on inner rings? What is the definition for complex loading?
Yeah, I think we need to split this into two sections, but it's also in two sections a question. So the deep cracks, I do not know what is the meaning, because we saw cracks in depth in the specimen, but we did not notice through cracking. I think this was the wording. So we had a 1 millimeter laser scratch, so which is already quite deep as an initial crack, and then we had some cracking. So I would say we had deep cracks on inner rings, which are the shaft specimen, but we had no through cracking. It not developed further in a way that the shaft was completely cracked through. Yeah. What's the definition for complex loading? Yeah, we added body stress up to 180 megapascal at the end. So the limit was 180 megapascal based on review, analysis, and simulation, and this was then added on top to the rolling contact fatigue.
Thank you.
Just a comment in detail, it is explained in the reports how we come to this megapascal, how we define the complex loading. So I hope this is, let's say, more in detail that I can explain it here as of today.
Yeah. Thank you, Jörg. And colleagues, we come actually to the last question, which I have here on my list. Okay, another one just came in. And this one is again from Scott. The question is, has there ever been a documented split planet pinion from a production aircraft that utilizes cylindrical roller bearings in lieu of spherical rollers as shown in the example? Jörg.
I can only say, to my knowledge, really to the limited knowledge that we have, we do not have all the knowledge of the aviation environment, especially not to the production aircraft if it comes to fixed wing, for sure not. But for cylindrical roller bearings, I cannot remember a case. But really, if I miss some, please do not get me wrong. Maybe Rodrigo or Rui know of a case. I cannot remember on a CRB solution having a split planet.
No. To my knowledge, I think the answer is no.
But I think you can say why you use this cylindrical roller representation. It was just a simplified way.
There are two things. The cylindrical roller bearings are used, for example, in, I would call it maybe older models, like the BO105, they have CRBs, for example. And cylindrical roller bearings are also used, I think, in other aircraft gearboxes. So I have seen it, but I do not remember a failure, a split from them. The failure on beams, I think the split that we mentioned, it's coming from the accident investigation. That is the only case I know. So this is really a limited knowledge, and it's for sure not 100% sure what I'm telling them.
Good. Thank you very much, Jörg. This is now again the last question from Marco. Marco writes here, to reduce the expected effort in investigating the RCF aspects, sizing and the related reduced stress values could be used as a design strategy to trade off with weight. Can we identify from the research results certain stress bands that can be considered far enough from RCF threats?
That's a good question.
I would say yes, but only for these specific bearings. Whether we can read them across to any other design, that's difficult to say. So for me, it's possible to do it. At the moment, the only way I can see this being done is that you do tests to demonstrate that your stress band is safe for your particular design, and then that's okay. Then when we are in a position that simulation for this is more mature and capable, it may be possible to do this just by simulation. But so the answer is yes and no at the same time, because if you want, you can define a stress band, but you also need to do testing to define that.
I mean, at the end, if you want to check maybe some aspects, you could use the same samples and the methodologies as used in the project. Try, let's say, some other stress ratios maybe to check if there is a different result. If we have maybe some, I would say, the through cracking that we have seen, if we reduce the stress, maybe we have a statistic that shows that the through cracking is not happening anymore. So this could be a strategy as explained by Rodrigo, but on the pure table now without testing, I would say it will be very difficult.
Yes. And also we have to remember that in these samples, and also I guess in most integrated bearing races, there is a very close relationship between the contact pressures and the body stresses. So by increasing one, you increase the other, and so on. So it's, of course, you can adjust your design to change the trade-off or the transfer function between those, but they are very closely related. So if you increase one, increase the other, reduce one, reduce the other. So of course, if you by going in one direction, it will help you anyway. So it can be done, but at this stage we cannot identify any generic design criteria to the level of detail of stress ranges.
Good. Then thank you both for that. There are no further questions. Then, colleagues, before we leave, perhaps advertising, Rodrigo, can you please go to
yes,
further?
Yes. Let's close this.
Colleagues, we have some further webinars coming up, which are actually as well final of the simulation event, just that you are aware of that. The first one was the one of today. That was the main gearbox project. We have another one actually tomorrow, also at 3 o'clock in the afternoon, CET, which is dealing with NORA. NORA is a model in order to assess actually aircraft noise, and this project was dedicated to rotorcraft noise. So perhaps we see each other tomorrow. We have then next week another final dissemination event, which is again dealing actually with a model, which is called AeroMS, and this one is used for market-based measures. So we'll see what kind of impact certain market measures may have on aircraft operations. There will also be actually a training event on the next day where you can get hands-on training on this new or upgraded software model. Then in April, there will be 3 final dissemination events. One is the Shepherd project, which is dealing with industry standards for drones and U-Space. And this project actually looked into a number of standards, industry standards, and assessed whether these standards could be used to comply with the regulations of several regulations in the field of U-Space. Then on the same day, basically it is a 2 days event, we will have the mental health project, Me Safe, which is dealing, as it is already mentioned, with mental health aspects. Was also linked or initiated actually by the German Wings accident. Will be a very, very interesting project, particularly for medical persons. And then, last but not least, there will be another helicopter or Rotorcraft project, the Helicopter Underwater Escape project, which is dealing with what kind of forces do you need in order to exit from a helicopter underwater. And really fascinating project as well. And you have here as well the link to the events page and to the registration. There is another slide which I will not comment anymore, but just that you know, colleagues, we are always looking into the future together actually with the member states of the European Union. We try to identify the key research priorities from an authority point of view. And you see here the topics which we have selected. We will, of course, provide this also to the European Commission, to the member state representative who are involved in Horizon Europe. And we hope that also in the future, EASA and other authorities in Europe can benefit from Horizon Europe funds for projects as this one. Mm-hmm. And now we come really to the end. For that, colleagues, I would first of all thank the speakers, Jörg, Rodrigo, Louis, thank you so much. Then big thank Jörg, you represent for me now your company. I know, Jörg, you have done a great job, but you have a great team also behind. And I would like to thank really everyone in your team for this great work you have done in the last 3.5 years. And colleagues, the difference here from the project as we manage them compared to other European research projects is that we do not only have this contractual management, we also have a technical guidance. And there I want to thank so much my 2 colleagues which are on my both sides, Rodrigo and Louis, who were the counterparts for Jörg's team and who worked together in order to make sure that we have all these deliverables now available. So the project is at the end right now. You find all public deliverables, colleagues, on the project page. You see here also the link to the project page on the EASA website. I can just only encourage you that you have a look into the public deliverables, that you please feel free to share this also with your colleagues, with your peers. And with that, I thank you very much for the questions you raised. I hope you got very good answers for that. And when I say this, I just see there's another question. I'm not sure. Please, to the webinars, does EASA issue an attendance certificate? Rogerio, I do not, but please send me an email. Perhaps we can solve it, okay? So, colleagues, thank you so much for that. I close now this webinar, and perhaps we see each other in one of the next webinars which are coming up.